We'll continue our discussion of linear models from class. Here's an outline, a little review of lines. The least squares fit. How good is our model? And there are two measures of that. And then we have an empirical rule type result, which you'll remember from statistics. And we also have some Excel functions along the way. So if you remember our coffee example from class, we had the demand in cups depended on the price, and it was a linear model. And this is a line, so the equation of D is a line, and we see that the slope is minus 15. Okay, so we can easily find the demand or estimate the demand given a price. And we did this in class. We just plug in 2 for P. And we saw the graph of D was a line. Now the slope, minus 15, that gives us a rate of change of the function D. If we increase our price by 2, then we'll decrease the demand by 30. Okay, so for every unit increase in price, we get 15 units decrease in the demand. Okay, so we can think of the slope as a rate of increase. Now we might have used some data to fit the line to get our linear model. So we're going to consider this cost production example from class, and we had Excel fit a linear model to our data here. So we can see that the slope is 64, or about 64.3, and the y-intercept is here. So we can see that if we increase production by 1 unit, we expect about $64 increase in the cost. If we increase production by 100 units, that would be about 64 times 100, or $640. So this is the model Excel came up with, and it's a linear least squares model, and we'll talk about how that how we get that criterion. And it gives estimated or predicted costs, right? So we can look in our model and use our model to find predicted values. Now, for example, when we've produced 873 units, well, our actual monthly cost when we did that was $80,000, but our model would predict about $94,000, and that's how you get our predicted value, which we denote y hat. And the 4 subscript just denotes that it's the 4th item in our list. We can find predicted values for all of the data in our list simply by using the linear model. So to do that, we want to access the slope and the y-intercept. So we can do that by using formulas for slope and intercept. So let's do that here. So we want to find the slope. And the syntax, you can see, is once you hit that open parentheses, Excel tells you what the arguments are. So the known y's and the known x's are called arguments of the function. So we want to highlight the, or select the y's. And I'm just going to take these, I'm not going to take that last value there, which is empty. Okay, so we want those, and now we want to separate with a comma, and now select our arguments, our next argument here. All right, so that gives us the slope. We can do the same thing with the intercept. You know, as usual, we start every formula with an equal sign. So we want intercept. And again, it's looking for the y's first, right? And then we want the x's. And that should do it. Okay, so now to find the predicted values, we want to take our x value, right, our independent variable, and multiply by the slope. And then we'd like to add the y-intercept, right? But now there's something wrong with this formula, because if I click and drag it, it's going to try to reference cells below this one here and this one here. So what we'd like to do, since we'd like to all of these values to reference these same values up here, we need to lock the row and the column. Actually, we only need to lock the row, right? Because we're not changing the column. But it's always a good idea. If you've only got one value that you're going to access, sometimes it's a good idea just to lock the row and the column. All right. But we don't need to do both. I'm going to do both here. Okay, so now when we drag that down, we're going to get the correct referencing, and you can click on a random cell and see that you are accessing the right values. Okay, so here are our predicted costs, right? So for our fourth entry here, our predicted costs about $94,000, and that's this value right here on the line. So when you have an Excel function or formula, the items that go in the parentheses are called arguments. Okay, so arguments are, for the slope function, we have 2 arguments, and they're separated by commas. So formulas have 1 or more arguments. How good is our model? Well, we can see that all of our values actually lie off of the line. So there's a little bit of an error here, and we can find out what those errors are, and those errors are called residuals. All we need to do is find out the difference between the our actual cost and our predicted costs. Those are actually the residuals. Calling it the error here, but we might as well call it the residual. Okay. So for example, our fourth item here, let's see, the residual is minus 14,000, and we can see that that value of 800 lies below the line, so it's a negative residual. Here's a graphical display. So our residuals are yi, which is the actual value, the cost in this case, and y hat is our predicted value. So it actually minimizes the sum of the squares of the residuals. So this is the residual, and we square them. So you might ask, well, why do we square the residuals? Why wouldn't we just want to add them up? Well, if we add up the residuals, let's come over here. If we just mouse over or select, if we add up the residuals, you can see the sum down here. Now that's 2.9. That minus 11 means times 10 to the minus 11. So this is really a decimal and 11 zeros and then 2 nines. So that's actually just 0. So it's not indicated exactly 0 because of round off error. But anything times 10 to the minus 11, that is interpreted as 0 for practical purposes. This is always going to be the case. Because this is a best fit line, the sum of the residuals will always be 0. And the issue, or what's happening, is that the positive residuals and the negative residuals cancel each other. So what we'd like to do is square them. All right. So we square those residuals, add them up, and that's going to give us an error. That's the error that's minimized by our least squares fit. And we can find, we can get a measure, and kind of an average of the sum of squares residuals if we just take this and divide it by n. And then we're going to take the square root because we squared it. And oh, by the way, we're not going to divide by n, we're going to divide by n minus 2. There's a technical reason for that. And it should remind you of the standard deviation, where we divided the sample standard deviation, we divide by n minus 1. Intuitively, it's just an average, and you don't need to memorize this formula. We're going to have Excel do it for us. So let's find Excel, find the, the standard error here. So there's a formula for that, and it's STEYX, and again we get the same arguments. So the known y's, and then we want the known x's. So if you forget which one goes first, well, Excel is just going to remind you here. See that? Okay, so this is like the standard deviation, but it's an averaged deviation from the line, not from the mean. So standard deviation is like an average deviation from the mean. Okay, so we have an empirical rule type result. So recall the empirical rule tells us a percentage of values that fall within certain standard deviations of the mean. Well, we also have the same type of result telling us the percentage of values that are one standard error of the predicted values. Okay, so it's our 68, 95, 99 rule. And then we typically consider anything more than 2 standard errors away to be an outlier. So this will help you do a couple of the homework problems in chapter 53. So let's first look at another measure of the goodness of fit. So we have the standard error, which gives us an idea of the goodness of fit. Also the R-squared value. The formula for that was rather technical, but we can just think of the intuitive interpretation is that it gives us a percentage of the variation that's attributed to our model. So if R squared was 1, that means 100% of the variation is explained by our model. That means our model is a perfect fit. And as with the other formulas, we have a formula in Excel to compute this. So let's go ahead and do that. So our R squared value is, it's just RSQ, and then we want known y's and known x's. So our known y's and known x's. So there's our R squared value. So about 69% of the variation about the mean of the y's is explained by our model. And that sounds pretty good. It's okay. Unfortunately, there's no rule of thumb for what is a good R squared value. Just bigger is better. Close to 1 is better. In the stock example in chapter 53, one thing that's kind of brushed over in the text is that, or in the problem, is that the R squared value is kind of low. Okay, you'll see that. Okay, so there's our R squared value. So let's do an example. And this is similar to one of the chapter 53 problems. We want to find 2 values that we're 95% certain that when we produce 600 units, that the cost is going to be between those 2 values. Now, how do we do that? Well, we need to find 2 standard errors of the predicted value for 600 units. Okay, let's find. Notice that 600 is not a value of our units produced, but it doesn't matter. Even if it were a value, we'd still be using the predicted value. So we're going to find the predicted value, which is this number here, just by plugging into our model. Predicted value is y hat. So it's that amount there. And we know that the standard error is this. So we want to find 2 standard errors. Okay, well that's simple enough. We just multiply by 2. So our range of values is going to be the predicted value plus or minus 2 standard errors. So it's this value, right? So it's this range. So if we subtract 27,544, we're going to get this, right? And if we add, we are going to get this. So that gives us an upper and lower limit for the range of values. With that, you should be able to do a couple of the homeworks in chapter 53. Notice that it's really analogous to a 95% confidence interval. The only difference is that we get a different interval for each predicted value. Okay, so we need to find the predicted value and then find the interval. Okay, and lastly, the linear models are special cases of regression models where we'll take into account several of the predictors. In this case, we just had the production as a predictor and the cost as a response. But you might have 2 or more predictors or independent variables.